You all now are familiar with what we call heating and cooling curves of a substance as it undergoes the changes of state from solid, liquid, and gas, which again, just to remind you, is a physical change. What we're going to talk about now is a very similar graph, but this one involves not just temperature, but also pressure, because pressure is very significant in the phase changes because increased pressure will actually decrease the likelihood of a phase change to occur. What I mean by that is if there's more pressure pushing on the surface of a liquid, then it's harder for that liquid to evaporate or boil. The same thing when it comes to a phase change between freezing and melting. If you have a higher pressure, that will change the temperature at which things will freeze and melt. So pressure is related to this, and it is quite significant. So that's what this graph that we're about to go over incorporates, not just the temperature, but also the pressure. So before we get too far, let me go ahead and tell you a little bit about a couple of things of vocabulary. The first thing is what we call a normal boiling point. The normal boiling point is what we, basically the temperature at which something boils at sea level. And that would be 1 atmosphere, which we just, generally call 1 atmosphere, or in torr, that's 760 millimeters, torr, or same thing, 760 millimeters of mercury, or 14.7 PSI. Those are all sea level standard pressures, and we call that the temperature at which it boils at that pressure is called the normal boiling point. Same thing with the normal melting point. Again, that would be when things melt, when it's under 1 atmosphere of pressure, okay? So let's go ahead and look at this first simplified graph before we go on to the next one right below. Notice the y-axis pressure, and on the bottom is your temperature, okay? So number 1 says, what is the normal boiling point for carbon tetrachloride? Okay, so our normal boiling point, we said, is at 1 atmosphere. 1 atmosphere in torr is about 760, which would be right about there somewhere, give or take, right? So if we're going to do carbon tetrachloride, that's say CCl4. I'm going to go ahead and draw a horizontal-ish line all the way to CCl4 the best I can. And then I'm going to look down to the bottom. That is not a very straight line, but you get the idea. So what is the normal boiling point? That would be, what would you guys say, about, I don't know, 85-ish degrees Celsius, right? It's a little bit of a hard thing to tell, but that's about 85 degrees Celsius. That's at 1 atmosphere, or the normal boiling point. So number 2, what is the pressure when water boils at 70 degrees? Okay, so we're kind of going backwards now. We have a temperature, we need to find the pressure. So 7 degrees will be right here in between. And I'm gonna go to water, which is right there. Wow, that's a squiggly line. And I'm gonna go over to the pressure, excuse me. And that looks pretty much spot on of 200 torr. Same thing as millimeters of mercury. Which liquid has molecules that have the greatest intermolecular forces? Interesting. Okay, so we have 3 substances on this graph, CHCl3, which is chloroform, CCl4, and H2O. Which of these has the greatest intermolecular forces? That would be this one. Why? Because, again, it takes the most temperature for a phase change to occur. CHCl3, chloroform, is going to go through a phase change at a much lower temperature. Therefore, its intermolecular forces must be weaker. All right, last. Increasing the temperature. Okay, so sorry, I misread the question. Increasing the temperature, meaning moving to the right, would that increase or decrease the vapor pressure? Okay, so let's just take water, for example. If I'm at 20 degrees, the vapor pressure is 0. If I'm at 40 degrees, it's still pretty much at 0. If I'm at 60, it will go up a little bit. If I go to 80, it will go up some. And if I go to 100, it'll go up quite a bit. Wow, that's diagonal. But you guys get the idea, that would increase. It's more or less a positive slope. Therefore, if I'm increasing the temperature by going to the right, then I would basically be increasing the water vapor pressure by going up. All right, so that's the basic gist of this idea of this graph. So let's go ahead and take this a little step further, and let's try an actual phase diagram. Sometimes this is called the triple point curve because there's something called a triple point. So what we have here, guys, is we have 3 states of matter on this graph. Every single time, this is going to be your solid, this is going to be your liquid, come on, and this is going to be your gas every single time. Solid, liquid, gas in that order, okay? Again, notice the temperature is still on the x-axis, pressure still on your y-axis. So a phase change between solid and gas would be right here. This line represents the phase change between solid and gas, okay? The next one we have here is solid and liquid. That would represent this line here. This is the phase change between solid and liquid. The next one we have is the liquid to gas. And again, that would be this right here. This is the phase change between liquid to gas. One thing I want to point out real quick, again, solid to gas is kind of weird. What that is called, again, as you should know by now, is called sublimation. That's like dry ice, which is solid carbon dioxide. When it sublimes, it goes straight from solid to gas. It skips the liquid phase, which again is why we call it dry ice. It's just a solid form of carbon dioxide. All right, so now that we know all that, again, that makes all pretty good sense. The next thing we can talk about is something kind of new. It's called the critical point. The critical point is going to be located right there. That's the critical point. It's always that upper rightmost dot. That is the critical point. The critical point is when your liquid and gas become indistinguishable. The pressure is so high and the temperature is so high that it almost occupies two states of matter at the same time. It is liquid and it is gas, and you cannot really tell the difference. That's called the critical point of a substance, okay? Again, liquid, I'm gonna say liquid slash gas phase, but let me just repeat myself. The critical point is an odd state of matter between liquid and gas when the two are coexisting and are indistinguishable from each other. You cannot tell which it is because it's kind of, well, more correctly is both. Okay, that's called the critical point. And again, it's always the upper rightmost point on these graphs. Typically, you'll actually show it, again, like it says here, or like it shows here, as an actual dot. Okay, the next thing is the critical temperature. The critical temperature, what you want to do is you find your critical point, which is right here, and then you're going to go straight down. The temperature at which the critical point exists is called your critical temperature, right there. That's your critical temperature. I'm just going to call it temp for short. The critical temperature, that is the temperature at which you reach the critical point, which again is when a liquid and gas coexist. Your critical pressure, you guessed it, is you're going to take the critical point and you're going to go all the way over to the left axis, which is your pressure, and that would be your critical pressure. Critical, oops, I misspelled that, pressure. Okay, again, it's all related to the critical point. As long as you know where this is, then straight down is your critical temperature, straight to the left is your critical pressure. Again, those are the temperatures and pressures at which you reach the critical point. And again, just repeat, that is where you have a liquid and a gas coexisting. One second, guys. All right, so the next thing we have here is what's called the triple point. Now, the triple point, I'm gonna go ahead and change my colors, is this junction right there. That triple point, which makes sense because you have three lines going into the exact same point. What that represents is when solid, liquids, and gases are all coexisting all at the same time. So the pressure is just right, and the temperature is just right, where the substance is in all three phases all at the same time. It's very hard to describe that because, again, on a daily basis, we don't really ever come in contact with substances that are at all three phases at the exact same time, but that is what a triple point is. So again, that is where you are in, let me go ahead and put it this way, solid, liquid, gas phase. Basically, again, all of them are coexisting all at the same time. That's called the triple point, okay? The normal melting point, again, remember MP is just abbreviated as melting point, would again be at melting, of course, is going on right here, right? This is melting. So therefore, normal melting point would be when you have 1 atmosphere 1 atmosphere is right here. I'm going to go over to my melting line. I'm going to go straight down the best I can, and that would be the melting point. In this case, it would be right there. That's the melting point, or the normal melting point, I should say. The normal boiling point, what I'm going to do is go from my normal line. I'm going to change colors from 1 atmosphere, because remember the word normal means 1 atmosphere or sea level. I'm going to go over here all the way to my boiling. Boiling is when you go from liquid to gas, so right there. And then I'm going to go straight down and right there would be our normal boiling point. Okay, so again, for the normal, all you do is you find 1 atmosphere, and then you go over to the melting line or freezing line, which will give you your normal melting point, which is in green, or the blue, which is your boiling point. You go over all the way to your phase change between liquid and gas, which is boiling, and then you go straight down to find that temperature on the x-axis. That's how you find your normal boiling point and normal melting point. All right, now that we have an idea of what all of this is, let's go ahead and try to answer some questions and see how we do. So the very first question we have here is, water vapor cannot be liquefied above what? So water vapor cannot be liquefied above what? So if I go above, let's see, in this case, we have 374 degrees Celsius. Why do I know that? Because again, 374 right there, if you go up, again, notice the liquid right here, this is liquid, that stops right there. So if I go to the right, I cannot stay in the liquid state. Remember that dot is finite, this dot right here. It's not a continuous line that goes on forever. It's a finite dead end, because we're going to reach the critical point, which again, just to repeat, is when the liquid and the gaseous states coexist. So above 374, I cannot have pure liquid, okay? Again, that's also the critical temperature, by the way. Number 2, on the water solid vapor equilibrium curve, which is right above us, what's the effect of increasing the temperature at constant pressure? Okay, interesting. On this curve, what's the effect? So the solid vapor equilibrium curve, solid vapor, okay? So what we're talking about is this right here. Let me go ahead and put it in red. So solid vapor, what we're talking about is this right here, solid to gas. Again, if I go this way, that's called sublimation. If I go this way, that's called deposition. Either way, we're looking at the red part of the curve because again, that is the solid vapor equilibrium curve. What's the effect of increasing the temperature at constant pressure? So if I go at this temperature and I go to the right, it will go into the gaseous phase. If I stay at this temperature and I go to the right, it will still go into the gaseous phase. Okay, so that's going to go to the gaseous phase again. From solid to gas, we call that sublimation. Skipping the liquid stage entirely and going directly from a solid to a liquid, sublimation. That's what would occur at that equilibrium curve if I increase the temperature at a constant pressure. All right, let me fix that B because it's bothering me. Okay, number 3, on the liquid vapor equilibrium. So liquid vapor equilibrium curve, that's this right here, liquid vapor equilibrium curve. What is the effect of increasing the pressure at constant temperature? So pick a temperature and increase the pressure. So I want to pick this temperature here and I'm going to increase the pressure. Okay, so it's going to go from gas to liquid. If I pick this temperature and I start to increase the pressure, again, it's still going to go from gas to liquid. Gas to liquid is called condensation. All right, so like I said, this is not terribly different than the heating and cooling curves, which you guys are already familiar with. What we're adding to this is the sublimation and deposition possibility going underneath the liquid, if you will, on the graph from solid to gas or gas to solid. What we're also adding, again, is the triple point. The triple point is where they all intersect in the middle of the graph, which is where, again, where solid, liquid, and gas phases are all coexisting all at the exact same time. Okay, it's a very delicate, precise condition of pressure and temperature, which again, we don't normally see on a daily basis. Finally, what we also have again is the critical point. The critical point is when the liquid and the gas phases coexist. and are indistinguishable from each other. Finally, if you can find the critical point and go straight down, that is your critical temperature. Critical point over to the left, that's called your critical pressure. All right, guys, I hope that makes sense. Please don't hesitate to ask, and thanks again for watching as always.